We're looking at molecules, so the molecular substances that we're looking at in the last topic. But before we can actually look at molecular versus the others, we need to know that it is going to be a molecule. And for that we need to understand the bonding that is inside it. And how do we make those choices on, oh yeah, it's a molecule, or no, it's covalent, or it's a covalent network, or it's metallic. This is the link to what we've done in the last couple of weeks. So, our giveaway for something being metallic, so having metallic bonding, so it's not a molecule, would be what? How do we know that it's metallic?
It's a metal.
It's a metal. So, therefore, how do we know that? By looking at its symbol, because we'll only get the symbol or the name in an exam question. So how are we going to know what it is? So how do you know that iron is a metal, so has metallic? How do you know that titanium is a metal, so has metallic bonding? Yep.
It's left of the blue line.
Cool. Okay, so there's a diagonal line in the periodic table, starting at boron, goes like that. Everything to the left of it and below it is a metal. Okay, so we're looking at things like iron, copper, aluminium, titanium, and so on. They're a single symbol, so if it was one of those with something else, it's not. So for example, titanium dioxide or anything like that, iron 3 oxide, anything like that, you're starting to go, if it's got an extra part to its name, then it's not a metal. But if it's just one of these elements, so that's the point I want to get to, if it's an element that is left of what we call the blue line on our periodic tables around the classroom, then it's going to be a metal. So it can't exist as a molecule. Okay? Molecules have got covalent bonding inside them. Okay? But they're not the only things that have got covalent bonding between the atoms. So if you find that something has a covalent bond, we've got two choices. It could be a covalent network or it could be molecular. So that's your first decision you have to make. The nice thing is this year we only throw 3 covalent networks at you. Graphite, which is carbon with carbon, diamond, which is carbon with carbon, and silica, SiO2. So they're the only 3 that won't be molecules if they have covalent bonding between the atoms. Let's go back to year 11. What is a covalent bond? What's happening to the valence electrons?
They are sharing.
Cool. We've got the sharing of valence electrons. And your choices here, as I've just said, are they could be covalent networks, or if you find this to be the true, it could be your molecules. And molecules is what we're really looking at. How do we know that electrons are going to be shared, not transferred or put into a sea of valence electrons like in a metal? How do we know if it's going to be a covalent bond? How do we know if a molecule or a covalent network is going to be formed? So it's good to know that they're shared. And last year you probably got a nice simple, albeit slightly wrong rule, or an incomplete rule.
If it's a metal.
If it's a metal, it'll be metallic.
If it's sharing with itself.
If it's sharing with itself, so say nitrogen with nitrogen, so
N2.
Yep, so N2. But it could be CO2, it could be H2O, they're molecules as well. What do we notice about the nature of those atoms in there? Which side of the blue line are they? CO2, H2O. Remember H is our exception to the blue line rule?
They're on the right.
They're on the right. So what class of...
Non-metal.
Good. So the simple rule is non-metal with non-metal. The annoying thing is that's not exclusively true. Now we get into this level of chemistry, we start to understand that some metal with non-metal bonds have got partly ionic nature and partly covalent. That's what we'll get to tomorrow. There is a way to quite easily work this out. Okay, but it is the sharing of electrons. The idea of today is to work out when are electrons shared and when are they transferred, because what is an ionic bond? It's the attraction between ions which have been formed by the transfer of electrons. So it's not the transfer of electrons that is the bond, It is the electric attraction between those ions which have been formed by the transfer of electrons. Okay, so And usually you would have said this is a metal with a non-metal, okay? Or a metal with a polyatomic ion like SO4 2- sulfate or CO3 2- carbonate. Again, how do we know when electrons have to be transferred versus when they can actually be shared? Well, what we have as chemists is we have a little tool or a little physical property that we can use to work this out. And it's called electronegativity. Now, electronegativity is, I'm trying to remember the scale, I think it's the Pauling scale. It goes from 0 to 4. So 4 is our highest number. 0, of course, being our lowest. This is the relative, it's got to be relative because we've got to measure it against other things. This is the relative affinity for bonding electrons. So the relative attraction for bonding electrons, or valence electrons. So, if a number is very high, it says that if it's involved in a chemical bond, it will have a really strong pull on these electrons. If the number is very low, it says when it's involved in a bond, it's not going to try and hold on at all. In other words, a very low value, these elements, things like cesium, rubidium, potassium, they're very likely to actually fully let go of those electrons to make a chemical bond, to make themselves more stable. So they become positive ions or cations, the ones at this end. And the ones at this end are very likely to pull on those electrons very, very hard. They've got a strong force of attraction for them. So what sort of ions are they likely to make? Anions, because they can actually rip the electrons off other things. Fluorine has an electronegativity of 4. The noble gases do not have electronegativities. We don't even give them the courtesy of giving them a number. We just say they don't have one, because for all intents and purposes for this year, they don't form bonds. Okay, that does change next year. Some of them are able to, but we'll get to that in 2017. So this is the relative attraction. Fluorine has the highest number. Look at where it is on the periodic table. And I'm just going to sketch that very quickly. Okay, these numbers don't have a value. Fluorine is here. It has the highest number. Which element, or whereabouts, do you think the lowest number would be? Bottom left? Cool. So there is a bit of a trend here. Electronegativity gets larger as you go this way, and it's because the nuclear charge is getting bigger, so more positives in the nucleus hold on to the electrons a bit tighter. And it gets higher as you go up as well. And the reason that it gets higher as you go up is that the bonding electrons are closer and closer to the nucleus, so the effect of that charge is higher. Something you'll look at in a lot more detail next year. But it's a good trend for you to have in case you're not given the values in an exam question. So what's the purpose of this? Well, what we have is an electronegativity continuum. So we say, I'm going to freehand sort this. We're going to look at the difference in electronegativity between two elements. If the difference is 0, this would mean nitrogen with nitrogen, oxygen with oxygen, sulfur with sulfur, chlorine with chlorine. So an element bonding with itself. If it's got a difference of 0, sorry, this is my difference of electronegativity. If the value is 0, you could expect those electrons to be what? Shared or transferred?
Shared.
Good, they'll be shared. So what sort of bond is that if the electrons are shared?
Covalent.
Covalent. Cool. Now we call it nonpolar covalent. What that means is the sharing is absolutely even. One nucleus does not get those electrons for any more time than the other. So this is a bit like when you're having to share something with a friend. You're likely to share it equally. You're likely to both get the same amount of use out of it. As we move up to this magical number, and this is not going to be to scale, I'm sorry, it's just not going to work for what I need to write in there. When we hit 0.5 for difference, one of the nuclei is holding the electrons for just a little bit more time than the other. Just a little bit longer. And what charge is an electron? Negative. So it's going to be a little bit more negative. Hence the term electronegativity. So they're still sharing, but this is like sharing with a younger brother or sister. You're going to share it because you have to be stable, for everything to be okay, not get in trouble with mum and dad. But one of you, the older one probably, is going to use it a bit more, get a bit more out of it. Okay? So for this, you create a slight, what we call dipole. One of the nuclei is slightly positive because it doesn't get the electrons quite as long as the other one. And the other nucleus is a little bit negative because it's got the electrons for a bit longer in time. So we create what's called a polar covalent bond. It's still sharing, but it's not sharing evenly anymore. Then we jump all the way up to a number 1.6. So when the difference in electronegativity is 1.6, actually about 1.5 to 1.7 is a grey area. You need to look at the physical properties as well. Up here, now one of the nuclei just cannot hold on to those electrons. They'll try and share, and then they can't. The one with the lower electronegativity has not got enough attraction on those negative electrons, and they end up being transferred to the other nucleus. So what do we think this would be called? Ionic. Very good. These numbers you are not given in an exam question. You have to know them. Okay? Now, just for your information, 0.4 is still classified as nonpolar covalent. The sharing is even enough, even if they're different elements, that we class it as nonpolar. But of course, one will be ever so slightly positive and one will be ever so slightly negative. 0.5 is classed as polar covalent. 1.6, so 1.5 we still think of being polar covalent, but 1.6 we start thinking of as ionic. It is a continuum though. So in this zone here, it's sort of got some ionic and some covalent properties. In this zone here, it might be polar covalent, but it's not strongly polar. So what does that look like? I'm going to need your help with this, please, on page 125. There are some numbers there. Sometimes you're given them in an exam question, sometimes you're not. So this is why it's good to know the trend. We're going to look at a very common molecule used to dissolve ionic things. So to dissolve ionic things, it has to be polar, which means it probably has polar bonds in it. So we've got water, H2O, and the way that it's bound is something like this. What are the bond types in this molecule? What are the bonds in there? What bound to what? Atom to atom.
Ion to ion.
Sorry?
Ion to ion.
Are they ion to ion in this one? What have we got there? It's a hydrogen to oxygen. Okay? So we've got two of these bonds. So we're just going to break it open to the OH bond. Okay? We're going to try to work out what type of bond this is. Now we know it's covalent because it's a molecule. We want to know whether it's polar covalent or non-polar covalent. For that we need the values on the page that you've got there. So, what is the value that it gives for hydrogen?
2.1.
2.1. And the value for oxygen?
3.5.
3.5. Awesome. Okay. All you need to do is take the big number and subtract the little number. Okay, so all we do is go 3.5 minus 2.1 and we get 1.4. Yeah? Okay, so the difference, so it's a triangle that's representing the Greek letter delta. or change in, yep, the difference of electronegativity is 1.4. That puts it around about here. So it means it's in the polar covalent section. We haven't quite reached 1.6, so it's not ionic. So therefore, this is a polar covalent bond. Now, one of you talked about it, something to do with ions in there. The fact that it's so close to this might help explain why water can react with water to make hydroxide ions and hydronium or hydrogen ions. It does have some ions in there because of how close it is to that magical 1.6 number. So it was actually a really good comment, even though it was technically wrong at the time. All right, it's actually such a big difference that it allows it to break up into ions sometimes, which is really good. Okay, now what we need to be able to do is also label which end is slightly positive and which end is slightly negative. The one with the higher number, higher electronegativity, has a stronger pull on those electrons. So it means that the bond isn't perfectly in the middle, it's ever so slightly to the right. Which means this end has got a slight negative side. But if I put a negative charge there, that would be like making it an ion. But it's not an ion, it's a molecule. So we use this funny looking S, which is actually a delta symbol. Okay, or funny looking D if you see it that way, which is what it's meant to be. Okay, so it's delta minus. Now, we call this a dipole, which means two poles. If that side's slightly negative, the other side must be slightly positive, creating our dipole. So, just going through what we're trying to achieve today, just recap. We are trying to understand whether something has got covalent bonds in it or not. Okay? Because if it's got covalent bonds, it could be a molecule. And this whole topic is about molecules, only about molecules. If it does have covalent bonds, that means the electronegativity must be between 0 and 1.5. Because if it's 1.6, it's ionic. Okay? If it's between 0 and 0.4, we call it a nonpolar bond, so we wouldn't put these things on it. If it reaches 1.5 or higher, then we do have to label which one is delta plus and which one is delta minus. The one that's delta minus is the one with the bigger number. Okay? This will help us then understand why molecules are polar or non-polar. Yep.
Like for example, there with the H2O,
yeah.
the H2, it's not 200, it's just straight the two molecules. The two.
So the H2O means it looks like this.
Yeah.
Two OH bonds. That's my last bit I wanted to get to actually, so thank you for mentioning. For those of us doing physics, we should understand about vectors. Vectors are an arrow showing the direction of a force or a velocity or anything like that. Okay? We can actually draw vectors for these as well. So we're going to show, and this is where we're getting to this in more detail in another lesson, but this has got a slight negative vector going that way, and this has got a negative vector going this way, and if I add those two together, I end up realizing that this side of the molecule is delta minus and this side of the molecule is delta plus. And this is why water can dissolve ionic substances, because the delta minus pole of the molecule can attract the cations out of the substance, and the delta plus side can attract the anions out of the crystal. Alright, so when we were looking at the explaining the solubility of ionic compounds, that's the reason why, but we'll get to that in another lesson. Key things for today: can you use the table of electronegativity on page 125 to work out if a bond is polar or not, or even ionic? If it is polar, can you label it to show the two poles? You'll notice that I've got rid of the other hydrogen. I'm only showing one bond. I don't need to show the whole molecule. Any other questions before I stop there? All right.